Okay, so let's move on to Chapter 5. In Chapter 5, we will discuss reflection and transmission behavior of wave incident on the interface of different media. And we will first introduce the so-called perpendicular and parallel polarization, which is something I believe that you haven't learned in undergraduate electromagnetics. So this is kind of something new to you. And the main reason for the discussion for perpendicular and parallel polarization is that their reflection coefficient and transmission coefficient are different when incident with an oblique incident angle. 也就是说，对于平行极化跟垂直极化的电磁波来说，它的反射系数、波的反射系数跟透射系数，在斜向入射的时候，有一个角度入射的时候，它的反射系数跟透射系数是不一样的啊，所以这一点其实在过去的电磁学里头应该是没有讲到过这件事情啊。那但是他们在正向入射的时候是一样的啊。The reflection and transmission coefficient for normal incidents are the same for perpendicular and parallel polarized wave. But this is kind of a trivial situation because when incident from the normal direction, you cannot tell is it a parallelly polarized wave or a perpendicularly polarized wave. Okay, the difference comes with an oblique incident angle, 斜向入射 oblique incident angle. And it results in two kinds of special behavior. One is the booster angle, which is only happens for parallel. Yeah. If my memory serves me, booster angle behavior only happens for parallel polarization. Only happens for parallel polarization. The booster angle means what? Have you ever heard of it? 有听过吗？ Booster angle means total transmission, no reflection. Okay? Now, booster angle means total transmission. On the other hand, critical angle is kind of the reverse of total transmission. Critical angle means total reflection, no transmission. And I believe you should be somewhat familiar with the critical angle behavior because the principal physical phenomenon for optical vibration, optical communication using optical fiber is based on total reflection. Okay, so to put it simply, when you incident from a medium with high permittivity to a medium with a lower permittivity, it's possible to have total transmission. 从高介链材料传播往低介链材料的时候，当你的入射角斜向的那个入射角度够大的时候，它就可能会遭遇到全反射的情形。So the total reflection phenomenon is possible from a high permittivity medium to a low permittivity medium, providing that the incident angle is large enough. It's steer away from the normal direction with a sufficiently large angle. Okay, then you may have if the incident angle is greater than the critical angle, then you will have total reflection. And we will probably stop at the critical angle for this week, and other subjects will be discussed in next week. All right. Previously in chapter 4, we have introduced the so-called RCP and LCP polarization. Now, left-hand circular polarization and right-hand circular polarization. We know that there are. It is the RCP and LCP is an orthogonal set of E-field representation, similar to perpendicular, similar to vertical and horizontal, or E theta and E phi. Because in the far field, supposing that the front door is the origin of the spherical coordinate system, then I'm standing on the horizon of the origin of the spherical coordinate system. So this direction, well, actually I'm pointing down is the E theta direction. Here the theta angle. If the z-axis is pointing upward at the door, then here I'm located at the position of theta equal to 90 degree, phi equal to whatever it is, all right, 0 degree, all right. Okay, so this is the x-axis. So at my position, the E theta direction is pointing downward. And E phi direction is what? You see a right-hand screw. Yeah. So if this is X, Y, and Z, so then the phi direction will be pointing. Okay. So the E theta direction and E phi direction form an orthogonal set of vectors, so that you can decompose the E-field direction of the propagating wave. Supposing that the propagating wave has already meet the TEM wave condition, which means that all of the E fields and H fields lies on the plane transverse to the propagation direction 所以当电磁波传的距离够远的时候，当它满足了 TEM wave 的条件的时候，它的电场跟磁场都会跟传播方向垂直嘛，对不对？而这个电场或磁场，你可以把它拆解成2个正交的方向所以像一般的球坐标系统里头，我们习惯用 E 西塔跟 E phi， 所以你只要有在做天线的模拟跟实作的话，你天线的场型的拆解，我们一般会用 E 西塔 E phi， 对不对？然后另外一种是什么 ？RCP LCP， 我们上礼拜讲过了，它也是可以，它也是2个正交的表示方式可以完全的表示一个 TEM wave 的电场方向只是说一个是右旋，一个是左旋嘛那我们今天要讲的 perpendicular 跟 parallel polarization 也是一个正交的可以拆解电场表示的方式只是说这一个 perpendicular polarization 跟 parallel polarization 的表示方式比较常用在不同材质的反射界面。反射或透射的界面然后伴随着你的入射角度我们可以把它做拆解那原因就是我刚才讲过的反射系数跟透射系数不同的So we know that there are several ways to decompose the E fields in terms of two transverse vectors. For antenna design, we use E theta, E phi, or ERCP, ELCP. For wave incidence on the interface of two media, it's convenient to use E perpendicular and E parallel because their reflection coefficient are different for the two components, right? So here, as I said, perpendicular and parallel polarization are particularly important for describing wave property across interface of different media. This is because perpendicular and parallel polarizations react differently on the material interface. So this is kind of this figure shows the illustration of incident wave, reflected wave, and transmitted wave at the interface of two media. So to the bottom left is the incident wave. So it's coming from the bottom left direction, and the interface is aligned with the x-axis, the vertical x-axis. So not the axis label. To the top is x, to the front is y, therefore to the right is z. It's the z direction. And you have the reflected wave going to the top left corner. You have the incident angle theta I and reflected angle theta r. They are defined with respect to the normal direction of the surface. So here we write n hat, okay? And as you learn from junior high school, the Snail's law 反射定律嘛，入射波跟入射角跟反射角是相同的嘛，那这个对于光的当然它最早是对于光传播的描述嘛，那当然你知道光也是电磁波嘛，所以 Snail's law 也对电磁波是有效的So the Snail's law, well, we actually have the Snail's law of reflection and Snail's law of refraction. So according to the Snail's law of reflection, the incident angle and the reflection angle are the same. All right, and the Snail's law of refraction, Snail 的折射定律 describe the angular dependence between incident angle and transmitted wave angle. And you know that they are related to the incident angle as well as the material property that we will describe later. So in this figure, you have the incident wave, reflected wave, and also the transmitted wave. Part of the incident wave may get through the interface and goes to the other medium on the right and forms the so-called transmitted wave. And the propagation direction of the transmitted wave also has a transmission angle theta t with respect to the surface normal direction. Okay, and what else do we have in this figure? Beta I, beta r, and beta t. What's that? They are phase constant vectors. Phase constant vector of incident, reflected, and transmitted wave. They are related to what? They are related to material property as well as the wave propagating direction. So the phase constant vector, beta, describe not only the wave propagating direction, but also comprise description about the medium property. Okay? And what else do we have here? The material property, epsilon 1, mu 1, epsilon 2, mu 2. Okay, as you already know that. And the very last thing that we should look into is the electrical field intensity vector and the magnetic field intensity vector. So let's starting from the incident wave. So the incident wave, the E field is pointing which way? This way, right? And you note that the E field direction is pointing outward from the plane expanded by incident wave, reflected wave, and transmitted wave. Have you noticed that the incident wave direction, reflecting wave direction, transmitted wave direction support expand into a planar surface? 入射波的方向，入射波的行进方向，反射波的行进方向与透射波的行进方向张出一个平面。事实上，也就是贝塔 R、贝塔 I、贝塔 R 跟贝塔 T 张出了一个入射波的张出了一个平面啊，在这个界面上。那这个平面它跟你的界面是垂直的嘛，哈。然后它包含了贝塔 R、包含了贝塔 I、贝塔 R、贝塔 T 三个向量。And in particular, this incident wave is referred as perpendicularly polarized incident wave because the E field direction, the vibrating direction of the electrical field, is perpendicular to the plane. 所以搞清楚那个 perpendicular 跟 parallel， 那个 perpendicular 到底是 perpendicular to what， 好不好？我自己大概念这个电磁学，大概念到第3遍的时候，我才记得那个 perpendicular 到底 perpendicular to what。我前2遍的时候，那个我知道 perpendicular polarization 跟 parallel polarization， 但是看到这个的时候啊，只要没标的话，我常常搞混了，我自己也常常搞混啊。所以你们当然第一次能记起来最好了哈。所谓的 perpendicular 指的是跟这3个入射、反射、透射3个箭头所张起来的平面垂直的那个方向，是我们的 perpendicular direction 哈，跟这个平面正交的那个极化啊，称之为 perpendicular。那反过来，假如电场方向是躺在这个平面上的话，那就是 parallel 啊。所以事实上，对于入射波来讲，电场是 perpendicular to the plane, but the magnetic field intensity vector is parallel to the plane. Okay, lies on the plane. And you should use your right hand to check if the drawing is correct. Alright, so E cross H provides you the wave propagating direction. So check it out. This way, so it's going top right direction. And as you can see, for the reflected wave, the E component is still perpendicularly polarized, and the H field direction is pointing upward. So it still provides you the propagating direction to the top left corner. And for the transmitted wave, okay, so you better check the drawing before move on to the next part of the problem. So this drawing is dedicated for perpendicular polarization, all right? So let's look into each component. So the first thing is the incident component, incident wave component. So let's look at the incident wave first. So the surface normal, the interface normal, is pointing to the negative z direction, right? So that's the positive z direction. This is the negative z direction because the wave is going from medium 1 to medium 2. So the normal direction of the interface is on the medium 1 side is pointing to the left, to the negative z direction. And okay, so the next is the E field description. So you can see the superscript I suggests this is the incident wave. The subscript, this the perpendicular sign. OK， 事实上我不太清楚，我不太晓得这个直接念英文要念什么了哦。所以我讲说 perpendicular sign. OK， so the subscript refers the E field intensity belongs to the perpendicular polarization part. And to the right of the equal mark is Y, means it's vibrating on the Y direction. Its magnitude is E sub 0, and its phase function is exponential minus J beta I dot R. So beta I is phase constant vector of the incident wave, and it's a dot product. It has a dot product with the position vector R. So R is the position of your observation point. Simply put, to put it simply, it's just the XAX plus YAY plus ZAZ, just the position. All right, and the beta I, the phase constant vector, provides the description for phase constant and propagating direction. So the first part, beta 1, is the phase constant. Is solely dependent of medium property 啊，所以 beta 1本身只跟材料有关嘛，由你的 mu1 epsilon 1来决定 beta 1。但是后面那个小刮弧就跟你的传播方向有关系啊。So the things in the small parentheses is the description for your propagating direction. So you know that on the XZ plane, okay, the incident plane, the plane of the incidence, reflection, and transmission is on the XZ plane. So for this angle, you can find its projection on the x-axis and the z-axis. 也就是这个红箭头，它在 x 轴跟 z 轴的那个投影量，可以拿来描述贝塔 I 的方向。那我要请你注意的是，那个红箭头的投影量在 z 轴是正 ，z 轴的投影是正的，是不是正的？然后在 x 轴的投影是正的还是负的？You should be careful about the sign of the projection. Okay, so for this particular red arrow, its projection on the z-axis is a positive. Is a positive 1, and a positive 1 for the s component, x-axis. And the amount of projection is dependent on the theta angle, theta I. So the projection on the z-axis is cosine theta I, and on the x-axis is sine theta I. So once you identify the projection, you can write up the vector for the phase constant for the phase constant vector part. And so as you can see here, beta I hat is the unit vector. But actually, the things in the magnitude of the things in the small parentheses is 1, right? Because it's the sum of cosine theta I and sine theta I, so the magnitude is 1. So you can put it as this. So this is the description of propagating direction, and this is the magnitude of the phase constant. And as we learned from chapter 3 and chapter 4, the phase constant, the magnitude of the phase constant is dependent of frequency and material property, like this. And what we learned from chapter 4 is that the magnetic field intensity vector can be found by cross product of the propagating direction and the E field description. So E cross beta divided by eta will generate the magnetic field description. All right. So using the formula that we have derived before, you can have the description for magnetic field intensity. So I need you to, it's kind of similar to the electrical field intensity vector, including this part and this part, because of course they are propagating in the same direction. But the difference is magnetic field intensity vector. Magnetic field lies on the plane, lies on the ZX plane. So you need to check up with this. Okay. So since the magnetic field is pointing toward the bottom right direction, so its projection on the z-axis is a positive number, and its projection on the x-axis is a negative number. So as you can see here, the projection sine theta I in the z direction and minus cosine theta I in the x direction. All right. And here is the this is the phase constant, not phase constant, phase function of the magnetic field. As you can see, because this is a product of the beta I vector with the simple position vector, so you end up as a scalar like this: S sine theta I plus Z cosine theta I. Okay, that's about everything of the incident wave part. So let's move on to the reflected wave part. So here we have the description of the E field, H field, and the phase constant vector, beta R. So the E field of the reflected wave is very similar to the E field of the incident wave. Its vibrating direction is on the y-axis. Its magnitude its phase function is exponential minus j beta r dot r. Okay, so you substitute beta I with beta r for the reflected wave. And the magnitude part, originally in this slide you have E sub 0 only. Now you have E sub 0 times gamma E perp. So this is, I bet you know that this is the reflection coefficient of the interface. And what B stands for? 我有点忘记为什么放一个 B 在那里。Okay, the subscript is perpendicular side, so you know that it belongs to the perpendicular polarization. 我还是没想起来这个 B 是什么东西。没关系啊，我们等一下看一看，我大概就会想起来了。为什么要放个 B 在这里？反正反射系数了反射系数。Okay, so just so you can see that the reflected wave is the magnitude of the reflected wave is the magnitude of the incident wave times the reflection coefficient, right? So again, the beta I is the phase constant vector of the reflected wave. So it's the product of material description, that is the beta I term, beta 1 term, and the propagating direction description. So it's AX sine theta r minus zx az cosine theta r. Okay, so you can identify that vector by looking into the red arrow and find its projection on z and x-axis. So as you can see, its projection on the x-axis is positive. 往 x 轴是正的. Its projection on z-axis is negative. So you have the negative sign here. And it's also described in terms of the reflection angle, theta. Okay. So you need to be careful about it that the projection of x-axis is theta I sine, sine theta r. Sine theta r. Its projection on the z-axis is minus cosine theta r. Okay. All right. And the content of the phase function is the dot product of beta r and position vector r. So it can be put simply as s sine theta r minus z cosine theta r. And you can also find the magnetic field vector in terms of this relationship like this. And as you can see here in the previous slide, for the incidence is z sine theta I minus x cosine theta I. Now, in the reflected wave, the H component will pointing toward the top right corner direction, so that its right-hand screw direction still follows for a wave propagating aligned with the red arrow. And because this is the product of the phase constant, the cross product of phase constant and the E-field description, so it also includes the reflection coefficient gamma B perp in its reflected in the description for the reflected magnetic field intensity. Okay? So the third part is the transmitted wave. Okay, so the third part is transmitted wave. So we're looking at the red arrow over here. So this is the transmitted wave, the E-field representation of the transmitted wave. As you can see here, its vibrating direction still aligned with the y-axis, and its magnitude becomes the product of E sub 0 with the transmission coefficient T B perpendicular. Okay, T the transmission coefficient, and the phase function exponential minus j beta t. So you replace beta I with beta t, and the phase part is still the product of beta t with r, the position vector. Okay, and similar to the previous two cases, the phase constant vector beta t is the product of the phase constant of median 2, that is beta 2, with direction description, that is sine theta t x plus cosine theta t z. That is the projection of the red arrow on the x and z axis. And beta 2, as we know, is a function of frequency, angular frequency, and material property. And you can also write the expression for the magnetic field following the same relationship. All right. Not the intrinsic. Here we have to replace the intrinsic impedance using eta 2. That is the intrinsic impedance in median 2, which is the square root of the mu 2 over epsilon 2. All right, so that's about the basics for transmitted wave, reflected wave, and incident wave. So now we can go on to find the reflection coefficient. Now, as you have seen in the previous two slides, the reflected wave is associated with the incident wave in terms of the transmission coefficient T, and the reflected wave is associated with incident wave in terms of the reflection coefficient, all right? And the two can be found with boundary condition on the interface. Okay, so again, we are looking to the total H field and total E field, total H field and total E field at the boundary. So let's look up at the E field first. So the first boundary condition, well, what are the four boundary conditions at the median, at the interface? 还记得吗？我们有4个 boundary condition， 哪4个 boundary condition？ Tangential E field continuous. Tangential H field continuous or discontinuous. Discontinuous 有什么条件？有表面电流。Suppose you have the surface current on the interface, then you can have discontinuous magnetic field, tangential magnetic field. You should have normal component. The normal component of electrical flux density can be continuous or discontinuous, providing what? They are surface charge on the interface. If there are surface charge on the interface, you are allowed to have discontinuous normal component of the electrical flux density. But for magnetic flux density, it must continuous always. Okay. Can these two become discontinuous? Yes, if you have magnetic current and magnetic charge. But we don't have that, so they must be continuous. Okay? 好，复习完了哈，那我们回到这边啊。So let's check up the tangential E field component first. They must be continuous across the boundary. That is, the tangential part of E2 and E1 must be the same, which can be expressed in this equation, right? You use the cross product of the normal direction of the normal vector of the surface of the interface. So the effect of this cross product is taking out the tangential component of E2 and E1. And so for E2, the E2 comprise the transmitted wave only. So you have ET over here. And E1 have two components, EI and ER. So it can be replaced with EI plus ER. And their location is at the interface, that is Z equal to 0. Okay? So you have So you actually can have the E field description in y direction and x direction because you have because the interface is expanded as the xy plane, right? 那个界面是在跟那个 xy plane 重合那只是说你只有 EY component， 你没有 EX component， 所以这就是为什么我们下面打叉叉的那个擦掉的那个是 X component 对于 perpendicular polarized wave 来讲，它只有 EY component for perpendicular incident wave, you have a EY component only, so the tangential part only associated with the EY components. Okay, because this is perpendicularly polarized, so it has no EX component at the interface, right? So the equation that we need to satisfy is this one, the circle one, EYT minus EYI minus EYR must equal to 0. And so let's get, okay, now I remember. The B stands for boundary, right? Gamma B and the TB stands for boundary. Because you can so if Z equal to 0 is the boundary, you can specify the reflection coefficient at the boundary, and you can also specify the reflection coefficient some way away from the boundary. This is the reflection coefficient. You can translate the reflection coefficient to a certain point before or beyond the boundary. Okay, so that will become有些东西像这个样子嘛，你们在传输线理论有学到，so the reflection coefficient at a certain point away from the boundary, from the actual boundary, can be expressed as the product of the reflection coefficient at the boundary with some phase shift,好，所以我想起来了这个 B 指的是 boundary。当然现在问题比较单纯就只有在看 boundary So we are focusing on the E field the total sum of the tangential E field on the boundary. So as you can see here, normal direction is written as Z direction, and the E field lies on the Y directions only, and their magnitude and the phase can be written in this function. So we can skip the vector part, and we have this relationship. This is the incident part, this is the reflection part, this is the transmission part. So we have our first relationship about incident field, reflective field, and transmitted field in terms of tangential electrical field. Of course, this is not enough to solve the two unknown, gamma B and TB, at the interface. So we need help from other boundary condition, from other boundary condition relationship. So let's check up with the magnetic field, tangential magnetic field part, tangential magnetic field. The tangential magnetic field continues as well, even though we know that it can be discontinuous as long as you have surface currents on the interface. But in this case, because the two sides are non-conducting, because both sides are non-conducting, so you don't have surface current on the interface. So you can safely say that the tangential magnetic field must be continuous as well. So we simply extract the tangential magnetic field part on the interface, that is Z equal to 0. So you have N cross H2 minus H1. They must equal to 0 because you don't have a surface current. If you do have surface current, you just put the surface current on the right-hand side of the equal mark. Okay? You can still help to solve the problem. So N is aligned with the Z direction, and H2 and H1, well, as you can see here, it has Z component in this way and X component. But the Z component is the normal component. In fact, it's the normal component. So the only thing that should be accounted for magnetic field is the X component part. So you can write HXT minus HXI minus HXR must equal to 0. 所以你的那个 tangential part 只有 X 方向只有一个双向。所以一样的，我们把反射系数、传输系数，还有它的那个角度的关系放进去。So this equation looks a little bit scary, I admit, but with careful examination, it's not difficult to understand. All right? No. Yeah, the math involved in electromagnetics are not very difficult. They are just messy. OK， 这是电磁学里头碰到的数学没有特别难其实没有特别难，它只是比较烦比较烦，要写好多遍，然后又写一长串但是其实因为是向量的关系嘛但其实它的内容并不困难。Alright, so we extract the X component, okay? So according to the previous slide, you can extract the X component. So you have the projection, cosine theta t, cosine theta I, cosine theta r. You have the reflection and transmission coefficients such as gamma b and tb. And yeah, and you extract the X component because the phase constant part you need to account for the phase component, the phase function part. But be aware that Z equal to 0 because you are only discuss the fields at the interface. So Z equals to 0. That will simplify your phase function representation somewhat. So you end up with equation 2, all right? It looks a little bit scary, but well, it's just 3 terms, all right? So you have equation 1 and equation 2. You need to solve for 2 unknown, gamma b and tb. So you are supposed to solve it as long as you know all the other parameters. So here comes the help of Snail's law. So according to the Snail's law, the equation is the combination of Snail's law of reflection and Snail's law of refraction. So if you look at the first part, it's the Snail's law of reflection. So you end up with theta I must equal to theta r. The second part is Snail's law of okay. The first and the last term combined is the Snail's law of refraction. So it's a dependent of incident angle and material property on the 2 sides. Okay. 所以上面这一个简单讲就是反射定律嘛，西塔 I 等于西塔 R。下面是 折射定律啊，相当于折射定律。So if you substitute Snail's law of reflection and refraction in equation 1, it can be simplified as this. It can be simplified as this. 这个当然你要自己试试看了啊，自己要试试看啊。And equation 2 can be simplified as this. So it's greatly simplified. Greatly simplified. But this is not enough. Equation 3 and equation 4 needs to be. So here is equation 1, equation 3 and equation 4. Equation 3 and equation 4 needs to be further combined to solve for reflection coefficient and transmission coefficient like this. Okay, this is your homework. All right. You need to deduct this relationship yourself. All right. Now you are supposed to do that yourself. Okay. But anyway, the result is kind of reasonable because it involves material property eta 1 and eta 2. It involves geometric relationship, that is the theta I and theta T. As you can see here, the reflection coefficient and the transmission coefficient are comprised eta 1, eta 2, theta I and theta T. And they are supposed to be known, as you know, as long as you know the material property and the incident angle. Okay, so cosine theta T is put here to simplify the expression. It can be translated into theta I with this relationship using the Snail's law of refraction. 所以你只要把那个折射定律套进来的话，事实上这一个西塔 t 可以被改写成西塔 i 只是你只要用这个套进去的话，看起来会有些乱看起来会比较乱 ，OK 就像这么乱 ，OK that this one looks a little somewhat more messy so we put it as the alternative representation, but I guess you can simply put this way to make it the representation for reflection and transmission coefficient more compact for perpendicular wave. So here is a reality check. If the incident angle is 0, that is a normal incidence. Then reflection angle is 0 as well. The transmission angle is 0 as well. Then the reflection coefficient and transmission coefficient can be put like this. For the reflection coefficient, it's eta 2 minus eta 1 over eta 2 plus eta 1. And the transmission coefficient is this, 2 times eta 2 over eta 2 plus eta 1. This is the same as what you have for normally incident electromagnetic wave. Have you, like you have learned in undergraduate electromagnetics, the format is also the same as what you learn from transmission line theory. Okay, so for normal incident case, the result seems pretty simple. The result is pretty simple, but it becomes complicated when you have an oblique incident angle. If theta I is not the same as 0. Okay. So let's break for 5 minutes. Okay, let's break for 5 minutes.